Hi everybody. Well, time to look at my ugly face again, huh? So this part that we're going to do right now, if you recall from the last video, or the last couple of videos I did, we've been working on this Rotel RA-1412 integrated amplifier. And the first time we went through it, we got some of the bugs worked out on it and we got it to function. But the next video we did the testing of the different factors. Total harmonic distortion. We did a Bode plot to look at the actual magnitude and phase versus frequency, and that was an interesting test. We did our square wave to check when we added reactance to the load to see if we got any kind of oscillation or ringing. We did a lot of different tests to check the different parameters of this amplifier. And what we determined was this amplifier wasn't working up to par. It wasn't working as well as it could have been working. So what we've done is, in this video, I've gone through and we found a couple of interesting things that we were able to repair that made the amplifier now perform as it should according to its spec sheet. And this amp never did have really crazy specifications. It's not spec'd out like my Pioneer SA9800, or as you've seen the AUX1 Sansui or some of those. This wasn't really designed to just have a whole bunch of crazy specs. It was really designed to be well built, long lasting, and be pleasing to the ear. And so even though, instead of having, sub-fractional distortion factors, this one, if you look, it says total harmonic distortion from 20 to 20 kilohertz is only 0.1%. A lot of people say that's too much, but honestly, I can't hear it. And anyway, this amp has a very sweet sound to it. I really like the way it performs. So we're going to see that. We're going to go through that in this video. I have a couple hours worth of footage, but a lot of it is just, running the camera and hopefully catching something interesting. So I'll get that condensed back down and get it into something that has some kind of a semblance of flow to it, and we'll see what we get at the end here. So I hope you enjoy it, and we'll see you again real soon. We have a lot of projects coming up, but for this time, Rotel RA-1412 for our last video. Thank you very much and take care. Hi everybody, welcome back. If you recall on the last video where we left off, we did some testing on this amplifier after we serviced it and noticed that number one, the overall THD, or total harmonic distortion, measurements for this exceeded what the service manual or the owner's manual specified this should be. And in addition to that, the distortion for the right channel and the left channel was different. One channel had a higher incidence of distortion than the other. And we broke it down, and it looks like most of our problem is in the power amplifier section, because if you recall, this amplifier, you can separate the preamp section from the power amp section and measure them individually, which we did. The preamp seemed to stay within specs of where it should be. The power amplifier, however, did not. So we're going to try to do a few things. Now remember, we did recap this. So there's your proof that just replacing capacitors isn't what's involved in properly restoring or servicing an amplifier. Sometimes the capacitors really have little to nothing to do with the performance if the capacitors are still in good condition. So in this one, the only one we did replace the capacitors in was the power amp, which was 4 caps. But all of the ones in the preamp we didn't touch, and as you recall, the specifications of the distortion versus what we measured were very good. This well exceeded and well was within tolerance of what we were supposed to see. So with that in mind, let's start with the amplifier section and look at a few things and see what kind of things we can do to improve the performance of the power amp section. At that point in time, we'll recouple it to the preamp with the little switch on the side, and we'll see how the overall performance of the amplifier is improved, and if we need to go any further with the preamp section or the tone control section or the line stage, whatever you want to call it, and hopefully get this thing performing as good or better than it did when it was brand new. If that sounds interesting to you, stay tuned. That's going to be this video. Alright, let's start with the DC offset. And where we're looking, we're using an oscilloscope this time, and we're looking at the speaker output right at the terminal where it exits the power amp board. And we're also looking at ground with respect to ground. And our first problem here, if we look at our scope, is it's kind of hard to read that, isn't it? And this scope tends to pick up a lot of noise, and it has to do with the way it samples and everything, but that's not a problem. We can fix that. So we're going to go into Acquire, and we're going to do an average. Now, if we're looking at a signal that's not changing very rapidly, you can do this, and this will clean it up, because this is going to take the average of that signal that you're reading. Again, when you have ultra low input levels at the input of an oscilloscope, this is what happens. And some scopes have are less noisy than others, but this one is particularly noisy, I've noticed. But that's kind of comes along with the territory. So if you look here, we're at 2 millivolts per division, and that means each block that this goes up, you're 2 millivolts off of your DC offset. It should be right here at 0 volts, and it is not. Obviously, you can see that it's not. So we're going to adjust the DC offset, which happens to be this pot right here, and we're going to adjust it until this is centered right at 0 volts. And you're going to find when I start turning this, it is going to be very, very touchy, and just touching this pot is going to make it flutter all over the place, but that's how these work. Okay, so we're going the wrong way here. We're going to go down. And you can see you move it and it drops down, then it comes back up, and that's the whole thing here. You just give it a little adjustment, wait for it to settle, and just turn it. Okay, I'm going to turn it again. We're just going to let it come back up and settle. And you see we're bringing it closer. And again, this is splitting hairs. You normally wouldn't do this. But we're going to see how close we can get this DC offset. That looks pretty good there. Oh, I think just touching that pot is so touchy. There it goes. Okay, that looks really good. And you can see it just creeps up ever so slightly, but we're talking 1 or 2 millivolts now. Okay, let's move over to the other channel now. I'm going to go here and here. And we can see that one is right where it needs to be. It is right on. Okay, very interesting. While I was looking at the waveform, you know, just to see what the DC offset was between the speaker terminal and the ground, I went to remove the probe so that we could measure some other points, and I felt heat. And this heat sink is really warm. It's almost like you were driving the amp at very high volumes for a long time. And I thought that was kind of strange. And then when I went to connect up the voltmeter to the bias point, lo and behold, when I turn the power on, there is 0 volts of bias voltage right now. So I think something finally has failed on this channel. I'm back looking at the DC offset. You can see we're hooked up using the voltmeter this time between the speaker terminal, and look at that. We now are up to a 0.5 volt of offset, and the protect circuit is not coming in. It's not letting the speakers connect because that's too much. Okay, I think I found the problem. I hope I can show you this, but see this 2SA or 2SC818 transistor right here. There's this one on this channel, and this is the channel that's acting up. And then there's this one on the other channel that is not acting up. If I take my finger, okay, and I place it on the transistor, just on the tab, I'm going to put you on the scope, and I'm going to show you what happens when I do that. First, let's put it on the tab of the channel that's not acting up. You can see really nothing happens. You get a little bit of noise, but nothing. Now if I go to the other channel, and you can see what happened. And just so I can show you what's happening to the current limiter when I do this, yeah, it draws crazy current. And the bias drifts, everything goes crazy. Now, what is that transistor, and why is it causing that problem? Well, throw the schematic in here real quick, and it's this one right here. So it appears as if we have a bad Q603. Now the big question that we have right now is, do we want to just replace the one bad transistor, or while we're in there, do we want to replace, you know, all of the small signal transistors? Now these drivers and the main outputs over here, I wouldn't worry a whole lot about. Those usually don't do that. It seems to be the smaller transistors that are low signal, low wattage, and high gain. Those are the ones that seem to do that the most. So I am most likely going to replace these, and when I do them, for instance this differential pair, I will match a pair of transistors, and I'll put a matched pair in there. We may even try to do something to thermally couple them. Just a couple things to make some improvements, but that's definitely causing problems, and I'm sure that's contributing to our distortion problem as well. And you can even see while we're sitting here talking, the other channel, which has been pretty rock solid all along, you can even see the DC offset has moved about 5 millivolts, which is no big deal, but as the amp heats up more and more, it happens. So they need replaced. We need to change the transistors. That's what this is showing us. So that's what we're going to do. Okay, I have a couple of KSA 992s set up in the test jig here. And if we go up to our scope, our pulses are nice and matched. And if we go to 2 millivolts per division, you can see the line pretty much right at 0, or not much off of that. So these transistors are very well matched, so I'm going to use this pair for this channel. Okay, all the transistors are replaced, and you can see the differential pair is now thermally coupled. Amplifier has been adjusted and is well heated. Let's first look at the waveform. I'm just driving the one channel that we're testing right now. Let's take a look and see. And if I turn it on, and I crank it up, and we're at wow, 148 watts, 130 watts per channel, which this is a 110 watt amplifier. So I'm actually kind of over pushing it a little bit. And distortion, yeah, even for overdriven. And if I just move down one click on my output, you can see we're below 0.1% at our regular 110 watts or whatever. That is more like what we wanted to see. Now let's just compare and put the other channel on. Okay, everything is set the same, but now we're just driving the right channel, which is the one we did not do the transistors in yet. And we're driving max power like before. And you can see we're all the way up to 0.8%, way higher. So those transistors definitely needed replaced. So I'm going to go over to the other channel and do the same thing. And we're going to adjust it, make sure the bias and offset is set correctly. And we'll see what our performance is like. Okay, it's been a few videos since we've done a solder and chat. So with that in mind, let's do one here, huh? And those of you who don't want to watch the boring, tedious process here, feel free to skip ahead. That's the beauty of YouTube, that you can do these things. But I'll be honest, I kind of get a lot out of this as well, because by talking like this to all of you, I've gotten a lot of insight from many of you on things that we've talked about. And so I've learned a lot of things too. And some of you have claimed that you've picked up a few things too by doing this. So I kind of enjoy it, and it gives me something to do besides the mind-numbing work of replacing components on a circuit board. And you might ask why I'm not using my desoldering pump. Well, on this kind of board, it's a little bit easier to do it this way, I think. Plus, I just don't feel like I have the larger nozzle on my desoldering gun right now, and I don't really feel like changing that either. That's kind of a dumb, lame excuse, but hey, that's what I got. I did remove these 3 pins up here, if you can see them, and they're just the input wires and the one ground return wire. And I did that so that I could get this board up out of here. I didn't really have to disconnect anything else, so that's good news. And I'm starting with this differential pair just so that I can get that out of the way, and then we will replace the other transistors afterwards. And if you noticed, I put just a little drop of flux on each of the pads that I want to remove here, because it just makes it absorb into the solder wick much easier, as you can see. And that just helps. And you can put it directly on the solder wick too, if you want. Either way works. But essentially this is all we're doing here. And then I'll just kind of bend these up, heat them up, and bend them a little bit if I need to. And then we should be able to take them out. You can unbend these leads, but since we're not reusing these transistors, I'm just going to cut them off so I don't have to worry about bending them. And if there's any solder stuck on the end of them, they won't get stuck pulling out, and they won't mess up your tracks. And the transistor will come right out. You can see that was pretty easy. I don't know what the focus is going to do here. I have the autofocus turned on. I probably could just set manual focus. Let's see what it looks like that. And it should stay, because I'm not going to move up and down very much with this, so hopefully it'll stay in for you. And then if I put my hand in front of the camera, it won't keep moving the focus on you. Alright. Yep, that one's still stuck. I have to clip it. go. There we go. And these two SA750s are pretty good transistors. I mean, I don't think they're not as bad as some of the other ones out there that we've had, but you know, like the two SA7s, what is it, 763s and things, they're not quite that bad. But this stuff isn't dry yet, so I'm gonna have to be really careful bending these leads that I don't pull this out of here. Once this cures, it's kind of, like I said, it gets kind of solid. Here we go. Oh, look, it's all squishing out on me. All right, let's see if we can get this to go in there. Ha! Good job, Tony. So I bent them the wrong direction. That's what you guys get for watching stuff that's free like this, you know? You're just gonna have to put up with what you see. Bend this off camera here. And of course, getting all this goop all over my fingers doesn't help any. That's the price you pay, huh? All right. This can be kind of awkward to do. Good grief. Well, I think I'm seeing the error in my logic here. The other one I did, I put this stuff on and heat shrinked it after I mounted the transistors, and it kind of leaked out and things like that. And I thought, well, maybe it'd be easier if I do it like this. And probably had I given this time to cure, my idea would have worked. But being an impatient individual like I am, that wasn't about to happen. It came out. There we go. Okay. I just want to make sure they're in there properly. Okay. All right. Yeah, that's not right. I'm going to have to clean this up and get another setup and do it the way I did on the other one. Stand by. Okay, I don't know if I can get everything contorted around there, but see, I have just a little piece of tape on the two transistors, and I bent the leads and then soldered it in, and I'll show you how I bent the leads. So I'll use the old transistor. Quit shaking. So what I essentially did was I bent forward like this and then bent back like this. And then you can see when you mount that in, it kind of pushes it back. And then I did the same thing on the other side, so that holds them back to back. Now that works pretty well. The problem is when we want to put our thermal adhesive on there, you'll find that it likes to drip all over the place and it's very messy. And so here's the thermal adhesive that I use, and unfortunately when you open this, I ordered this on eBay, and it dries, it starts to cure when you open the bottle, or the tube, and so once you open it, it doesn't last a really long time, so you have to kind of seal it up, and don't buy big tubes of it. I bought this really cheap online, and it works really well. And what it is it's a thermal adhesive. It's silicone with thermally conductive material in it. So you just spread it on the device that you want to couple together, and then it drips all over everything and makes a mess. So you have to hurry up and put your little piece of heat shrink that I dropped on the floor. You just open it up, and I put this over it. Then you take your heat gun and you shrink it. And it should fuse this all together. And there you go. And then what will happen is, I'll pinch that shut. And let me see if I can get the camera in there at an angle that you can see it. Just like that. And that thermally couples those together to make them a little more thermally stable so they track a little better. Alright, let's get back over here. Let me clean up the mess. And that definitely worked better than my last one I tried. So I'll just keep my original plan. Okay, let's continue, shall we? So now we're going to replace, let's see here, these two transistors down here. These are NPNs, and you can see they're directly coupled to the output of the differential pair. And here's the thing, it's hard to troubleshoot some of these types of amplifiers. If you notice, all of the stages are connected directly on a DC level. In other words, there are no capacitors separating the different sections of the amplifier. So you see your drivers, you're coming straight out of your drivers, it goes directly into the base of the outputs. There's no coupling capacitors like you would see in, for instance, a tube amplifier or in a capacitor coupled amplifier as per se. Now, that is a really good thing as far as performance, but what it will do is, if you have one of these transistors fail, say something shorts, everything connected to it is subjected to that short as well. And that's why it's quite often in this type of generation of amplifier, one transistor will go, but you'll see a chain reaction and a whole bunch of them will be blown at the same time. And that's why, because they're direct coupled. A lot of people see where an amplifier is advertised as a DC amplifier, and a lot of people think of DC in terms of direct current. But really what they mean by DC is direct coupled. That's actually what that means. And when we talk direct coupled, that's what it means. You don't have capacitive coupled amplifier. And there's, like I said, there's advantages as far as frequency response and distortion and things like that, but the amplifier is subject to, if something shorts, well, it's like Christmas tree lights, you know, the old Christmas tree light string that was in series, you know, one goes out, they all go out, they say. Well, it's kind of what happens to these things, and you go from having one bad transistor to having a catastrophic failure, and transistors, resistors, diodes, everything goes at once. And we've had a few of those in the past here. And, well, what can I say? Comes with the territory. You want to work on these types of amplifiers, you're going to see that type of failure happen from time to time. A lot of people ask, why do you work on this old stuff? You know, there's so much new things, and it's not too long into the conversation before the word digital comes up, and I think digital causes confusion sometimes with people. And what do I mean by that? Well, digital doesn't mean that it's perfect. Digital doesn't mean that it can't fail or that things can't go wrong. So, one thing, for instance, a digital recording of something. Okay, it's recorded at a certain bit rate, and I know a lot of people hear about all these terms. You have bit rate and bit depth and so forth. But what a lot of people don't realize is a lot of people think just cranking up the bit rate makes it sound better. And that is not always entirely the case. As a matter of fact, increasing the bit rate can sometimes give you more distortion, because the bit rate can limit the amount of the highest frequency. And, you know, when you talk about the Nyquist rule and all that, it's limited by your actual bit rate. And that's an advantage in some ways, because if you get too far above the human hearing range, things that are above the human hearing range, you can actually have intermodulation, distortion, and things take place, and you'll actually get harmonics below the fundamental, and it will creep down into the audible spectrum, and you will actually hear that distortion. Whereas if it was sampled at at the proper bit rate, like 44 kilohertz or 48 kilohertz, you wouldn't see that. Now, that's not something that happens all the time, but it's just an example that all of those things can affect the sound, and just because it's digital and just because it's high bit rate doesn't mean you're going to get a perfect representation of the music as it was recorded. Remember, what you're recording quite often is analog, and you're converting it to digital, sampling it, and then converting it back to analog. And that process, if it's done properly, can be superior to analog, because you don't have wow and flutter, you don't have, you know, a lot of the things we deal with in the analog world, but you can have other types of problems like aliasing and that takes place because of intermodulation at high frequencies and things like that. So without getting into much more detail, digital isn't always isn't the end-all answer. It still has to be executed properly, or it's still not going to work right for you. And quite honestly, once it comes out to your speakers, it's analog. So really, it's still an analog signal going into your speakers and coming out of your speakers and going into your ears. So all things become equal at that point. And the whole thing is, if it's executed properly, whether it's analog or digital, you can have really amazing sound. So don't cash this stuff off. It's very high build quality that you can't get today, or at least is very expensive to get. And it can perform as well as the modern equipment, or better in some instances. Alright, so here's the transistors I'm replacing. These NPN transistors are 2SC1628s. They're difficult to find a replacement for these because most transistors in this package, they always will have the collector in the middle. So you'll have base collector emitter, or emitter collector base, or something like that. This one has the base in the middle. It has the emitter base collector. Odd pinout. And the only solution, there are transistors that are very good substitutes for this, but the pins are different, and you're going to have to swap pins around, bend them around one another, which I don't like doing. But Central Semiconductor, I found out, and these are still available, makes this series, and it's a pretty close match to those. And this is the CEN-U10, and these seem to work as a good replacement to these. So that's what I'm using on these. Now, these are a little bit pricey. You can't just buy bags full of these. They're upwards of $5 a piece or so, unless you buy large quantities, which gets very expensive. So unless you have a real need for these, they're not worth buying just to put in stock. And unless you really need to replace them, or you know, they're not worth buying because it's a lot of money. But in this instance, I'm glad I'm using them because you can see it did make a big difference swapping these all out. Now, I don't know that these are high failure items. I've never really worked with them a whole lot because they're not real common. So, you know, should you just shotgun these and replace them? Well, I can't say that you should or shouldn't because, again, this is something that I haven't worked with these a whole lot. I just know that if I replace these, then I'm not going to have to worry about having any problems with them for a very long time. Alright, I'm going to tack these in first and then straighten them out and then finish them. We still running on the camera? Yeah, we are. Okay. Put this on. Alright, so take a look here. Now, something you have to be cautious with these is the tab on them. See how these have a tab sticking out the top? The new ones, the tab is longer, and these are so close proximity that they can bend. When they're like this, they can bend and touch. Even the old ones could do that. And these are still tied to the collectors. They're hot. So if they touch, you're touching the two collectors of those two transistors together. So you have to be careful. Don't let the lead length too long, and make sure they're spaced properly before you solder them in. Now what I'm going to do, now that I have them centered where I want them, I'll cut the leads before I finish soldering them. And I'll leave them a little bit proud of the board so that the solder has somewhere to build up onto. Get rid of this stuff here. All right. Okay, let's see if we can get this in here now. And I'll do one last touch up on that. Hey, looks good. And then just if you want to follow up, I use a little cut down brush, paintbrush, with some anhydrous isopropyl, and I clean off all around here like that, and it just makes it look a little neater. Not necessary, this is non-corrosive, but the flux that's in this solder, but I still like to clean it up. Makes it look nice. Alright, where shall we go next? So let's do this one here on the bottom because it's a little bit tricky to get to, this one down here. The other thing is, if you put flux on this, don't put a whole lot so it runs all over the place, but even if you just use a little bit, you're still going to find out that it gets on things and it will get on your fingers, and your fingers will get all sticky and you'll have to clean them. But I don't care. Doesn't bother me. Alright, let's see if we can clean this off here. And we'll have to go back and touch up some of the things that we hit with this solder braid by accident. Okay. Alright. Get a little more light on the subject. What do you think? That just covered it right back over because there's so much solder on here. I try not to go too crazy with that because it's bad for the tip of the soldering iron, but I do use it a little bit to move things around. By the way, these tips on these Hakko irons, you can see how much I use them, and I get a good 3 to 4 years out of each tip, you know, so they're pretty high quality, I have to admit. They last a very long time, especially if you keep them clean and take care of them. This iron has the advantage that when you park it in its cradle, after a little set period of time, it'll cool down, but not totally. It'll drop to a lower temperature that's not detrimental to the tip. So it's not sitting there burning the tip all day long. If you leave it plugged in and turned on all day, it won't hurt it. And that actually makes a big difference in how long the tips last on these things. Okay, that's loose. So I'll trim those pins off again, if I can reach in there. And I'll bang the camera and make you all dizzy. Okay. And there it is. And this one is a PNP transistor. It's a 2SA818. And for that one, I will use this CEN-U57. Okay. So, same thing. And notice the tabs are longer on these, so you have to be careful that they don't hit anything. But other than that, it's a pretty good fit. All right. The lead's bent on this a little bit. Kind of awkward bending around this camera, but you guys are worth it. We'll do it. All right. So we'll tack it in again. Nip these off just a hair. And we'll solder them up. Let's see if we can get this whole pad here, because we pretty much cleaned the whole pad off. And then I'll clean this one, resolder this one, because I cleaned it off with the wick. Alright. And let's clean it up and see what kind of job we did. That's the other reason I like cleaning the flux off, is that once you do that, you can see the quality of the solder joint you made, and if you need to go over it again or not, because sometimes you have to clean it off and do it again if you don't get it on there right. That looks good. I'm going to leave that. Alright, so what I'm going to do now is I have just a couple more I have to do on the top here, which I will do. And we're going to put this back together and give it another test. Okay, I have this all back together, but I'm not going to let it off the leash yet. I'm going to put it on the current limiter. I have this meter connected to the bias, and this one connected to check DC offset. And don't worry about that negative 13 millivolts. That's just noise that it picks up from the speaker leads. I'm going to plug this in, make sure it's on limit, and turn it on for the first time. And you definitely want to bring it up, on some sort of a current limiting device, because you just don't know, if you got it all right. I mean, you can check your work 100 times and there could still be a mistake in there, so you want to be very careful. Putting it on a current limiter isn't going to make it impossible for something to fail, but it will make it more difficult for something big to fail. Alright, let's turn it on. Okay, so far so good, because the light dimmed way down. And we should have somewhere between 500 and 600 milliamps, and right now we're idling at 474 milliamps. We have 36 volts of bias, and we want, or millivolts, I'm sorry. And that's with the current limiter on there, so we have the voltage is dropped a little bit as well from the bulbs. So I'm going to turn that down just a little bit here. And again, they're going to be different because we put new transistors. They may have a slightly different gain than the old ones that were in there. And then we're going to set our, just rough in our offset right now. Again, this is going to change once we put full power to it, but I don't want to see if I'm going the right way. Maybe I'm going the wrong way. No, I'm going the right way. And the DC offset is a lot better position for this pot. It's centering more than it was before. So that kind of gives me a good feeling. And you have to wait for it to settle, and it's going to move around and so forth, but that's pretty good, 1 millivolt. Okay, now that we have these to a decent level and we know they're responding to adjustment, that means that most likely our transistors are all in correctly and they are working correctly, and the amplifier is at least functioning somewhat. So now we're going to go to full power, and you can see that this is going to come up a little bit, and we want it to be 30 millivolts, so it's pretty close right there. And this we're going to adjust just a little bit. You have to let it settle. And I mean, when you have 1 millivolt or 2 millivolts of DC offset, it's really not a big deal. Look at that. Wow. How often do you see that for offset? Now, our bias is going to keep creeping as the transistors warm up, and that's what it's supposed to do. So we're going to just turn it down another little hair, and we're going to just watch it. And I'm just going to let it creep up and give it about 10 or 15 minutes to settle. And then once it does, we'll do a final adjustment on this, and then we'll be ready to see if we made any difference with our distortion. Okay, just going over this once again, we want less than 0.1% at rated power. So let's see if we can get that. We did have it on the other channel. Let's see if this channel is now straightened out as well. Here we go. Everything is now warmed up, so it should be what it's going to be. And look at that. I'd call that 0.1 because it's 0.095. So it's just making its spec. And the waveform looks really good. Everything looks good. And I think that's, at least with the unit open and everything the way it is, that's about as good as we're going to get it. Now, it may get a little better than that once we close everything up, put all the covers on, redress the wires, and so forth. Because if there's any little amount of hum or anything in there, that will introduce some distortion. So I think we got it. And it's definitely meeting its specs even with all the covers off. So I'm happy. Way better than, what was it, 0.4 or 0.5, or the other channel was like 1 point something, I don't know. So big improvement. Let's put it together and clean up the bench and see the final results. Alright, amplifier is all back together and it is connected, and I have everything but the top cover put on. And let's just do another quick analysis of what happened to our distortion now with everything connected the right way and put together. And bring the volume up. I'll show you where we're clipping. So right there, we're looking at what? There's 100 and, what is it, 109, 110 watts? 109 watts. Let's take it right up to clipping right there. 127 watts, okay? Let me turn that back down. And let's see. Let me get you moved over to the distortion meter here. And yeah, that looks really good. We are well under our spec. And if I go down just a little bit, one click on the volume, and you can see it drops substantially. And if we run it at a reasonable power rating, let's say there's about 40 watts per channel, and we're looking at about 0.03, you know, and that's including the distortion built into the test equipment and the cables and everything else. So for total distortion, I think that's spectacular. Well, it's all together, and I am way happy with it. It's working great, and it's sounding great. I got a bunch of songs I ran through it, and performing perfectly, no hiccups, no nothing. And I don't know, let me see if I can find some sort of song here that's YouTube safe somewhere. Let me put something on here. Okay, well, we can't play Another One Bites the Dust by Queen, but we can play this. Well, anyway, you get the point. It works, and of course I'm recording this through my lapel microphone because I just don't feel like setting up all the microphones just so that you can listen to it through your speaker in your cell phone, through YouTube encoding, and yeah, and then everybody can tell me that it doesn't matter anyway. So, you get the point. It is working very well. I quite enjoy it, and this amp's ready to go. So I guess what this shows is that the transistors in an amplifier can fail with age, and they can somewhat affect the performance of the amplifier. You have noise, you have shot noise, you have hiss, you have all kinds of different failure modes of transistors, and all of those things can add up. Capacitors aren't the answer to everything, although a lot of people think that it is. And although I believe that older amplifiers should be recapped because capacitors will leak and will fail and can damage the board, as we've seen in like the Adcom GFA 585 series. But when they fail, it doesn't always necessarily mean harmonic distortion. What you see is degradation of frequency response, or you'll see areas, you know, in the frequency spectrum that have dropout compared to the others. The amp won't be real flat. But you can recap an amp and really not address the problem at all. There are many other factors, from the simple things like cleaning the contacts, making sure the controls are clean, making sure that you have good contact between your speakers and your, you know, your input jacks and so forth, to more mundane things like what we saw here, bad transistors or misalignment of, you know, either the offset or the bias or things like that. So there's lots of things you really have to diagnose an amplifier. You can't just replace capacitors. Although replacing capacitors to me is a maintenance item, but I equate that to replacing tires on a car. The tires may be able to get you where you're going. They may get you there, you know, without knowing any difference from a new set of tires. until you hit that spot on the road where you need the good tread on the new tires, and then you'll see the difference. Capacitors work in a very similar manner. So again, that's just my 2 cents worth for what it's worth, and that's about all it's worth. Anyway, this was a fun project. I have a whole stack of components that I want to go through, and I mean, when I say a stack, I mean we're good through well through the end of the year. So I'm going to go on to the next project. This one's going to be buttoned up. It's ready to go. And until next time, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Take care. Thanks. Bye-bye.